Good morning or good evening. How are you all doing? Hope everybody's doing well. Welcome. Welcome, Professor Gao. And
good morning. Good morning.
Good morning to all of you. Pleasure to see you.
Same here. Yes. Herbert, can you right click on my name and make me a co-host so I can help you manage?
Okay, I appreciate it. Is your name in Chinese now? Let me see.
No, it's in English.
Okay, I found it.
Just right click on it and make me a co-host, not host, co-host.
Yeah. Okay. Let me just get it. It in Spanish it says make you host.
There should be an option to make me a co-host, not just
yeah.
But
that doesn't matter. I can make you host, no problem. Is it?
Yeah, you can make me a host. I'll make you a co-host.
Okay. Good.
Okay. Fantastic.
Now you have to enable me. Okay.
I'll get rid of the waiting room so people can just get in.
Good.
Yeah. Hold on. Oh yeah, for some reason today I don't have the co-host option. There must be somewhere else.
Yeah, that's what I couldn't find it.
Yeah. But I'll help you unmute everyone.
All right.
张瑞文，开始上课了吗？不然呢？每次都是9点开始。
我海燕，你在这会开吗？
Okay.
Yeah. Just let me say a few words in Chinese, so they ask them to feel free to ask questions. 大家好，欢迎参加我们的今天的第3讲。Sira 教授，我们继续这个课程啊，一共7讲，今天第3讲。然后中间大家如果有什么问题的话甭管是用英文也好，用中文也好，都可以提问。如果这个是中文的话，我可以帮你翻译，好吗？我们下边就请Sira 教授继续给我们做讲座。好，谢谢大家。Yeah, please feel free to ask questions. If you don't feel like to ask questions in English, ask in Chinese, and I can help you translate it into English. So feel free to inject, to interrupt, to make sure that you understand, you follow the lecture. Okay, so yeah, so Herbert, is all yours. Thank you very much again for your wonderful lectures, and we look forward.
Oh, you're welcome. It's a pleasure. It's a real pleasure. It says that I cannot share my screen because the host has not enabled me.
I just enabled it. Sorry, I will find a way to. I think when you set up the meeting, you go to next time before the lecture, you go to the website where you set up the meeting, and can make me a co-host.
Okay.
From there, so from that point on, every lecture I can help you manage it. Otherwise, we can also do this on the fly.
Okay.
And Raphael and Christoph are also here. These are scholars from Poland. Raphael, you know him very well. Christoph is getting his PhD. He did some research on ADRC as well. So welcome.
Welcome, Christoph, and welcome.
Good morning. Thank you very much.
Yeah. Pause, stop. So it's already being recorded, right? Herbert, you already start recording the lecture when you get in, right?
Yeah. I'm not habilitated now, so I cannot do anything.
No, yeah. I will make you the host at the end of the meeting, so the recording will be sent to you, just like last time.
Okay.
Okay. Unless there are any questions, we'll get started. Just one more chance. Does anybody have any questions to ask Professor Sira Ramirez?
Good. Everything's
All right. Go ahead. And maybe we have about 90 minutes lecture. Maybe at 45 minutes or now 1 hour mark. Maybe you can stop for a few minutes to see if anybody has any questions.
okay.
Great. Thank you very much.
Thank you.
Thank you.
All right. Let me recap. Can you see the screen?
Yes, we can see it. Yeah, go ahead.
Okay, last time we introduced a state coordinate transformation for nonlinear discrete time systems in order to uncover the hidden linearity that might be prevailing between the input and the output structure of the system. This is the case of single input systems. The case of multiple input systems is pretty much the same for those systems in which this can be done without the need of some extension of the system. So what we had last time is that given an input-output structure, that input-output structure is linearizable by means of this state coordinate transformation, which involves the output, the advance of the output, and several advances of the output all the way up to a certain number R, which we call the relative degree. Once we set up these nonlinear functions and the control input appears explicitly only at the rth advance of the output, then it's very easy to show that this part of the transformation is constituted by independent functions whose gradients are linearly independent, gradients with respect to the state variable. So this part of the transformation can be used as a new set of coordinates. And then all that remains to be done is to complete the transformation by means of additional independent or functionally independent scalar functions whose gradients are independent among themselves and also independent of the first R1, of the first R coordinates. So the thing is, there is always enough freedom to define this additional set of coordinates. When we want an additional constraint on these coordinates by demanding that their first advances does not explicitly depend on the control input, that is not always feasible. That might not be possible. And we will see through an example why is that and how to proceed. So this is a standard state coordinate transformation induced by the input-output structure. And when you perform the transformation, you get a linearized subsystem which is driven by this nonlinear function, by this nonlinear function of the, oh, I'm sorry, by this nonlinear function of the input. So if we further assume that this function has a non-zero partial derivative with respect to the control input, then we can locally solve for an auxiliary variable that acts as a new input. Let's call it V, and that V completely linearizes this part of the system. Of course, the zero dynamics will always be present there for those systems in which this transformation is not complete all the way down to the n variables. The zero dynamics will be the dynamics ruling this part of the system, which is somehow detached from the input, and because we have chosen that to be the case, and it's uncontrollable, and it's also decouplable from the output itself, except for the relation that these variables might have in the conformation of this nonlinear function. So let's call these variables the zero dynamics variable. The zero dynamic variables integrate this nonlinear function of the control. So the definition of the auxiliary control input as this entire nonlinear function actually depends on the variables of the zero dynamics. And of course, it depends on the linearizable part of the system, the linearizable coordinates. So with that in mind, we went ahead and we explored the possibilities of completely linearizing part of the system. Naturally, if the whole, yes, she can.
Yes, can you go back? Can you go back? Some student asked for references. Isidori canonical form, is this the one that in the nonlinear control book that he wrote?
Yeah, the continuous part is sort of parallel to this, so it will help him very much to understand this because there's a strong parallel. Isidori also worked out the discrete time case in one of his many publications. I forgot which one it is, but I do remember I have a paper on using this canonical form for discrete time systems that's written long ago. I'll make it available.
Okay.
I recently rediscovered it because I had no idea. I had worked in this area many, many years ago.
Yes, so this is rather important, but also obvious and also clear here. So in the dynamics of system, discrete or continuous, you have state that can be influenced by the input, and you have state that cannot be influenced by the input. So so that explains the difference between the zero dynamics from the actual dynamics that can be controlled. So this is true for both analog and the discrete, right?
Yeah, yes. I should make only a very little remark on what you said, which is absolutely correct. The influence of the input that we're talking about here, because it's a structural problem, the influence of the input we talk about is the explicit influence of the input, in which you see the input in that part of the model. Here, of course, you don't see the input because you have chosen to make all these variables so that the advance of those variables are independent of the input, and sometimes you have enough freedom to do that. But of course, the input is influencing everybody because all these variables are comprised of two parts: the part that is linearizable and the part that is hidden somehow. So all those variables are here in this CK. CK is the vector from C1 to Cn. So the input is indirectly influencing this. But in the structural problems, what we seek for is explicit appearances of indeterminates, i.e. variables. And if that if that appearance can be guaranteed to be explicit, then we have a structural property. Here, the structural property is made explicit because the control only influences this ladder of inputs, this ladder of variables. And of course, it can be made controllable from an auxiliary input that comprises all these nonlinear functions. All this is linear, and this is what we have in this slide. All this is linear. But this is nonlinear, and this Z contains the first RCs plus the etas, this which is here. So you do have an influence of this part on this part. And you have an influence of this part on this one, but it's an implicit, it's not explicit influence. It's an implicit influence that can affect you. And we will see how the instability of this part of the transform system can affect your control design from here on, even though the immediate effects are not seen in this part of the dynamic or in the output, are not seen, but they will be felt sooner or later if eta is unstable. It will turn out that you don't have enough control to continue detaching this part of the dynamics from the linearizable dynamics. In a coming example, is that clear?
Yes, thank you. Thank you.
Okay. So this is the situation. We have part of the system which is feedback linearizable by means of a simple state coordinate transformation joined with an input coordinate transformation which depends on the state and allows for the possibilities of continue controlling the system through an auxiliary control input. So the rest of the dynamics, of course, is let's say quote unquote autonomous in the sense that it depends on the initial conditions of all the state variables, and it evolves without any explicit influence of the control input. Now, for instance, if we wanted to stabilize this part of the system by means of the control input VK, which is an auxiliary control input, the problem reduces to a very simple problem. You have this dynamics, which is a pure time forward dynamics or time delay dynamics influenced by the auxiliary control input. So a linear state feedback would be enough to control the system. Remember that all these advances of the output are ultimately functions of the state. And therefore, as we explained in the first lectures, causality is not really damaged here because you can always resort to a transfer function representation of your controller and your closed loop system, and everything will be fine from that viewpoint. The feedback is determined in the usual way, but by demanding that the closed loop characteristic polynomial of the resulting difference equation is Hurwitz, or I should say it has all the roots inside the unit circle in the complex plane, which is centered at the origin. So the standard stabilization problem is solved by means of linear feedback, and that is granted by this structure. Of course, this structure can be low dimensional, as we mentioned, because the zero dynamics is relatively small. Or it can be full dimensional if the zero dynamics coincides with the order of the system. Therefore, the variability of this dimension of this linearized system depends on the output essentially, and how many advances you need to obtain the explicit appearance of the input. That's the relative degree thing. And the relative degree can go from 1, in which you will have a one-dimensional linearizable subsystem, all the way to n, in which you will have a fully feedback linearizable subsystem, a full dimensional feedback linearizable system. The the trajectory tracking problem is essentially the same in nature, except that instead of stabilizing the output, you will stabilize the tracking error of the output. If this is an output reference trajectory denoted by y star as a function of time, the tracking error is simply the difference between the actual output and the reference trajectory. So the model for the tracking error is just a copy of the original model of the system, except in error variables: output tracking error, control input error. The control input error in this case is defined as the difference between V, the auxiliary control input, and the inverse of the system from the input. That means the K plus R advance of the output in nominal terms. So this is the output error. So now we have dynamical structure that we had in the stabilization problem, and therefore what we need to define is an input. Sorry, we need to define an input variable, which is represented by the input error, in order to do the feedback based on the tracking errors. But essentially the problem is the same. So when we substitute this input error by means of this expression, you will have the full form of the controller. So it's linear feedback of the tracking errors plus some pre-compensation. This pre-compensation or inverse of the system is obtained from the nominal reference, output reference trajectory. Therefore, the two problems would be solvable in this very simple structure: stabilization, trajectory tracking. And what we have shown in the last lecture is that the dimension of this system is independent of any state coordinate transformation, and of course is independent of any input coordinate transformation, which is defined on the basis of the state. So it's an invariant. This dimension is an invariant. The relative degree is invariant with respect to input coordinate transformations, which can be viewed as partial feedback with the possibilities of continuing having control options on your system by means of this auxiliary variable. And the invariance of that is very well established. As I believe we already saw, the input-output structure doesn't vary because the state coordinate transformation for the relative degree number of variables is precisely the same. So let me move this out of the way. So the Rth advance of the output viewed as this composition map continues to be independent of the new input, and the relative degree is preserved. So zero dynamics will also have the same feature. I mean, the zero dynamics cannot be changed by feedback because the relative degree cannot be changed by feedback. And if you do a state coordinate transformation, that will be the case. I was wondering if we had already seen this in detail in the last lecture. I believe we did, right?
Yes, go ahead, Professor.
So we were already doing examples, right?
That's cool.
Okay. So state coordinate transformations like this one that we have put here, which is invertible, does not affect the relative degree. And here is the explicit computations that allow you to conclude that the input-output relation has the same dimension and that the relative degree is preserved. So it's very nice. And the zero dynamics, of course, the nature of the zero dynamics cannot be changed by feedback. Remember, it's only indirectly influenced by the input, and that influence is not even explicit in the equation. So it's very hard to see that that there would be a way that you could modify this. In general, you cannot. And therefore, the stability of that zero dynamics becomes an issue, becomes important, because the zero dynamics, if it goes unstable, it will provoke, through the control input definition, an influence of the zero dynamics variables on the feedback constitution. Therefore, the feedback will be affected and you can saturate it. We made the distinction between a system that has only one equilibrium for the zero dynamics, and that equilibrium is stable. We call it globally minimum phase. If that equilibrium depends on the initial condition of how far you are from the equilibrium, and it becomes unstable, and that can easily happen in discrete time systems, then you will not have globality of the minimum phase behavior. If you have some unstable equilibrium, or only one unstable equilibrium in the zero dynamics, then it's globally non-minimum phase. If you have combinations of stable and unstable equilibria for the zero dynamics, then all sorts of behaviors might happen, including oscillations which are very reminiscent of chaotic dynamics. So the issue of the stability is very important in terms of the zero dynamics. Let me explain that through a couple of very simple examples. Suppose you have this nonlinear system, which is nonlinear because it has this single nonlinearity. And the output, let's assume the output is the sum of the two states. So this will be my first state coordinate in a transformation that will try to uncover the linear part of the system. So yk is the first coordinate, is C1 of k. The advance, the first advance of this output will be just the sum of these two advances, which already contain the input. Therefore, the advance of the output is an explicit function of the input. Therefore, the relative degree is 1, which is non-zero. Therefore, there is only a one-dimensional dynamics between the input and the output that can be categorized as linearizable. The rest of the dynamics has to be obtained via complementary functions that have independent gradients of the first output. And so if we take, for instance, C1, which is the output, I am forced to take the output as the first state variable in this transformation. The gradient of this function is just the row vector 1, 1. So I can take any other vector whose gradient is independent of this vector 1, 1. And one of them could be, for instance, 1, 0. A function which has a gradient 1, 0 would be x1 plus some constant, or x1 itself. So this is a transformation that will bring out the linear part of the dynamics only to the first equation. This is a second order system, so the first equation is linearizable. The second equation in the second variable, which is x1, is independent of the input, and therefore it qualifies as the zero dynamics in the way that we define it. So it's very, very easy to stabilize the system by means of controls. I can get rid of this nonlinearity, and I can impose some asymptotic behavior on the closed loop system. But the zero dynamics always remains there. It will proceed to adopt a form in which this C1 finally either converges to 0 or to a constant value or tracks a trajectory, but the zero dynamics will be in this dimension. And of course, the way to stabilize this system, just to show you how the design that I make, no matter how reasonable, is not immune to the instabilities of the zero dynamics. So I can get rid of the nonlinearity and impose some linearity by means of linear feedback of the first coordinate, which is just the output. This control will cancel this nonlinearity and will join forces with the presence of C1 here in order to make the closed loop system be C1k plus 1 is 1 plus alpha C1K, something like that. Yeah, 1 plus alpha C1K. So if 1 minus alpha C1K, I meant to put here minus 1 minus alpha C1K. So if 1 minus alpha is between minus 1 and 1, alpha has to be between 0 and 2. And therefore, the zero dynamics will eventually converge to this nonlinear dynamics. Sorry. The zero dynamics will converge to this nonlinear dynamics. This nonlinear dynamics has an equilibrium point at eta 1k equals to 0. And if I start at 0, this dynamics, it will continue to be at 0 forever. So it's an equilibrium point. To find out whether it is stable or not, I can proceed in several ways. I can proceed by linearization, and I can proceed by Lyapunov functions. But what is clear here is that there is some region of attraction of this equilibrium eta 1k equals 0. And if you're far away from that equilibrium, let's say that we start with eta 1k equals 2. If eta 1k is equal to 2, or the initial condition for eta 1k happens to be 2, when I am satisfied with this behavior of the closed loop control system, eta will start increasing towards negative and positive values, which are growing in magnitude very quickly, because the nonlinearity rises them to the cubic power. So if eta 1 is increasing positively and negatively, that is affecting my feedback. That is affecting this part of my feedback, which is acting by cancellation. And therefore, there will arrive a moment in which I no longer have physically available controls to be able to implement such a large quantity that eta 1k cube is representing at that particular period of time. So UK will saturate physically, and it will deteriorate. In the meantime, because of this cancellation, before the saturation happens, my closed loop dynamics is very nice. It doesn't depend on eta, it doesn't depend on anything else, but on my design constant alpha, because I was able to drive this, I was able to drive Z1 to 0 by means of this feedback. But this cancellation is hurting me when eta 1 is growing in an uncontrolled fashion, because there is no control here to ease the growth of eta 1. So this is how the zero dynamics might affect your design, and therefore one should take care of that. This is another example in which you have a similar situation, that you have controls everywhere, and the output is just the first coordinate. Of course, this immediately tells you that the system is relative degree 1. And so this is the first transformed coordinate. The output itself has to be the first state coordinate in the transformation. And because the relative degree is 1, I only have a one-dimensional linearizable subsystem. And the rest of the variables can be prescribed in such a way that UK does not appear in the next advance of eta. So if I take the difference of these two quantities, it is clear that I am going to eliminate the control, and therefore the difference of these two quantities will have an advance that does not depend on the control. So this is also a nice complementary variable to the linearizable output variable, because the gradient of this function is 1, 0, and the gradient of this function is 1 minus 1. 1 minus 1 is independent of 1, 0, as the gradient of the elements in this transformation. Therefore, this qualifies as a coordinate transformation to exhibit the canonical form. And doing that is very simple. You get this this one-dimensional linearizable subsystem and a one-dimensional zero dynamics. As you can see, the zero dynamics depends on the linearizable coordinates and on the complementary coordinates as well. And the linearizable system might require you to eliminate nonlinearities that in turn depend on the zero dynamics. So the zero dynamics, in this case, if I manage to stabilize C1 to 0, because this is essentially a linear system in which I can get rid of these nonlinearities, if I can stabilize this Z1 to 0 by means of this feedback, which is clearly the feedback that allows you to do that for any alpha between 0 and 2, then the zero dynamics will evolve towards this autonomous dynamics. This dynamics has a zero equilibrium point, and the stability of that zero equilibrium point is guaranteed as long as the initial state of this dynamics is chosen between -1 and 1. If the initial condition for eta 1 is chosen outside this open interval, then this goes unstable and very rapidly grows in a potential manner towards unstable negative values. And when that happens, your design is being affected because this cancellation term will be growing very fast, and therefore, physically speaking, you might not be able to sustain this control action because it requires controls that you don't have available, and therefore the whole control scheme is jeopardized. But of course, you will not notice anything strange as this eta grows, because you have blocked, by means of that cancellation, you have blocked the influence of the zero dynamics variables on the closed loop system. And therefore, that growth is unobservable in the linearizable dynamics. And at the same time, that growth cannot be influenced by the control input because it's already been defined to stabilize the first part of the system, and you have no further controls available. And therefore, eta 1 is uncontrollable. But this is how the instability of the zero dynamics might eventually affect you, because you won't be able to physically continue implementing this control law due to enormously large values of the zero dynamics variable. Now, let me give you another example which has a more physical content. This is a boost converter circuit. It's a continuous time system which discontinues right-hand sides. So the variables I sub L, which is the inductor current, and the voltage across the condenser are continuous variables, in the sense that they might not be differentiable, but they are continuous. And they are not differentiable because the right-hand side is discontinuous, the right-hand side of the differential equation. These circuits enjoy an average model, and we're interested in the average model. The average model contains control sources. This switch acts as an ideal transformer. And that ideal transformer, it makes the interaction between the input circuit and the output circuit very simple in terms of these ideal lossless transformers. So the average dynamics, which furthermore we have normalized here to get rid of the L and the C and the R, the normalized average dynamics assumes that your control U somehow takes values in the real line and not in the discrete set 0, 1. Average values of the DC to DC power converters were introduced many years ago by Slobod and Chuk and his associate, Professor Middlebrook. These state average models are very convenient because you can you can proceed with design for the nonlinear system. And it's nonlinear because the control is multiplying the state variables. This average normalized models of the dynamics is very convenient to do analysis, even though it is rather idealized. This Q represents a normalized resistor. This one represents the normalized voltage source. X1 is the normalized current, and X2 is the normalized voltage. So X1 will be the normalized current here, X2 the normalized voltage. The control is substituted by a pair of control sources which act as an ideal transformer between the first part of the circuit and the second part of the circuit. And all of the parameters disappear. This becomes a 1, this becomes a 1, L becomes a 1. That's the nature of this model. Well, this model is nonlinear. And if we take the output as the output voltage, which is convenient because I might be willing to use this output voltage to feed an electric motor or something like that, or some load. This output already is a state of the system, and it contains the influence of the input, even though in a nonlinear manner. So this system has an output which is relative degree 1, because the next value of the output, the advanced output, already contains the input. So this will be the linearizable dynamics in the system. And this has to play the role of the zero dynamics. But as it is, the zero dynamics in this particular case is still depending on the input. And as we were saying in the canonical form, we should be able to get rid of this control input for convenience. It's for aesthetic reasons and for ease of analysis. But of course, you can also analyze the stability of the zero dynamics when you know that you're applying some feedback to your linearizable part of the system. And here we will have a little surprise when we want to get rid of the U in the zero dynamics model. So let's take the output voltage as the first state variable in the transform system, and the second complementary variable for the zero dynamics will be X1. So nothing will change. We just reshuffle the names of the states, and what used to be the second state now is the first state. What used to be the first state now is the second state. So we have essentially the same equations in new variables, but this is the linearizable part, and this is the zero dynamics. In order to get rid of U, I could dream of another variable in which if I multiply, let's say, the first equation by Z1, I will obtain the quadruple product delta U eta 1 C1. And if I multiply the second equation by eta 1 at time k, I would have here also the same quadruple product with a minus sign, delta U C1 eta 1. So the addition of C1K plus 1CK plus eta 1K plus 1 eta 1K will get rid of the control input. That's fine. The only problem is that I perform the operation using variables in the future. So I have to find the primitive of that expression. By primitive here, we are using the same language as in calculus. The primitive of any function is just the integral of the function, but here we talk about the primitive of that function being the one that has the next value coincident with the one that I just chose. So let me explain to you here in my iPad what happens with this example. Okay. I guess you cannot see my iPad.
No, not really.
Okay. Well, now it's gone. Well, okay. Now it should be there.
Yep. Got it.
Okay. Here's what happens. Let me rewrite those equations. You have x1k plus 1 equals x1 of k. This is the first equation. Plus delta minus, sorry, I think it was plus uk x2 of k minus 1. And x2 k plus 1 is x2k plus delta uk x1 of k minus x2k over q. This was, sorry for my handwriting here. So I have a minus sign here. Is that all right? I'm sorry.
That's okay. We can see it.
Okay, if you multiply the first equation by x1, you'll get this factor, and the second equation, x2k plus 1 by x2k, you will have an expression in the right-hand side which is free of u. U will not appear because the sum of these two terms after the multiplication will vanish. And you will have only a function of x1 and x2. But now the problem becomes the following. I have to find a function eta1 of k. I have to find this function eta1 of k, which is my complementary variable, such that eta1 of k plus 1 is this, is the whole expression there. Right? That's called, I have to find the primitive, because that expression upstairs is completely free from the control input. And therefore, my zero dynamics expressed in the variable eta1k has to be such that the next advance of eta1 is independent of u. And I found a variable that does that. Eta1k would be given by something like this. x1k minus 1 plus x2k minus 1. That's the primitive. x2 comma, x2 comma, these are commas here and here. Now, the problem is this. These two variables, x1 of k minus 1 and x2k minus 1, these two variables are not state variables. They are the preceding value of my state variables. They are one step back. variables from my state variables. What does that mean? If they are not in the model, I have to create them. And in order to create them, I have to define a couple of new variables. Let's call them, let me erase that. Yeah. Let's call them x3 and x4. So x3k plus 1 would be x1 of k, so that x3 is just the previous value of x1, and x4, k plus 1, has to be x2k, so that x4k is x2k minus 1. These variables are not part of the description of the system. These state equations come from x3 and x4, which are not part of the description of the system. So what it means is there is not an invertible state coordinate transformation in this example that will get rid of the control input in the zero dynamics. Because if you want to build that variable whose next advance is independent of the control input, you have to resort to variables which are outside the system. They are called exogenous variables. These variables are called exogenous, and they are part of an extension of the system. The new state is defined in terms of the internal state of the system, but the new state is not part of the system. It's foreign to the system. This is only a memory device. X3 and X4 will only be able to remember the immediate past value of X1 and X2 respectively, but they're not part of the system. They are part of an exogenous transformation. They are part of an extended dynamics transformation. So what it means simply is that in this converter, the state coordinate transformation that will produce the canonical form exactly in the way that we prescribed it with a linearizable input-output dynamics and complementary variables which are not controlled and which are not observable, that part of the dynamics cannot be made independent of the control input, because you require a higher dimensional system with new variables that were not in the original system in order to be able to find the primitive of that transformation in the state space. You see, the primitive of that transformation requires something which is not in the state space, which is only comprised of X1 and X2. This is very important. This is very important because it has a parallel with dynamical feedback linearization. It's only the integrability, quote unquote, because in discrete time systems, we should talk about summability, in continuous time systems, we talk about integrability. The summability or the integrability of the required variables takes you out of your state space in order to be able to do it. Okay, let me go back to let me get rid of that and go back to the slides. Are you seeing the slides now?
Yes, go ahead.
So this is an important feature that will pop up when you want to study dynamical feedback linearization. It doesn't mean that this cannot be statically feedback linearized. Of course it can. It only comes up because you were insisting in having a zero dynamics outside, a zero dynamics which was independent of you. And that requires, quote unquote, the solution of a partial difference equation. That partial difference equation has a solution, but the variables in which it is solved are not in the state space of the system. And therefore, the transformation, the state coordinate transformation that would identify the linearizable part and that would produce the zero dynamics variables independent of the control input is not possible in this example because you require exogenous feedback. You require the presence of exogenous inputs. And that is pretty much the case in dynamical feedback linearization. By that I mean systems which are not linearizable by static feedback and that you require some addition of variables. You require some extension, and that extension is known as an exogenous extension of the system in order to be able to completely linearize now the extended dynamics. Okay, but let's continue with the example. So we carry on with the fact that the control input cannot be eliminated in this second order system because we need a fourth order system. And the fourth order system only has two variables that serve as a memory device to remember the immediately past values of these two state variables. But that's only a minor consequence because we can still analyze the stability of these dynamics when we do some feedback that brings my output, which is the output voltage, to a constant value, let's say. And all this is in the average sense, which is still valid. It's an analysis which is valid because it's the actual value of the equilibrium will be that. So let's assume that we have as our objective to have a constant value of the output voltage, which is C1 in this case. And it's very easy from these equations that the equilibrium point, let's say the equilibrium point for eta 1 will be obtained when these two terms are equal. I mean, when eta 1 does not vary anymore in time. So these two cancel in equilibrium, and therefore U times C is equal to 1. The control is just the inverse of the output voltage in equilibrium. So if the output voltage goes to V, then U becomes 1 over V in equilibrium. And U being 1 over V, you can compute the equilibrium of eta 1 in terms of the equilibrium of C1, which is V, because these two terms also cancel in equilibrium. So you have this situation. The zero dynamic variable has this equilibrium value.
Can I ask a question here?
Yes, please.
So on your previous slide, I understand you need to resort to some exogenous state space to do the feedback linearization.
No,
but I'm wondering.
No, sorry to interrupt you. Not to do the feedback linearization. No, that isn't necessary. Just to get rid of the control input in the zero dynamics explicitly. Just to get rid of U in the zero dynamics explicitly, I would create a new variable that is not invertible in this state space. That's all.
Okay. So, but is this because of the feature of discrete system, or it is because of this particular system? Well, so what I'm saying is, if you consider the original continuous dynamics, so it seems to me, well, you can introduce a new variable by x1 square plus x2 square.
No problem.
Yeah, but if you go back to the original continuous system, do you still has this, well, how should I call this feature, or do you still have to resort to some exogenous state space to do this thing, or?
Yes, you will have to when you go back, because this is precisely what I was trying to use here. I was multiplying C1k plus 1 by C1k and eta 1k by eta 1k, which is somehow the analog of the derivative of C1 square.
Right.
Quote unquote. So yes, you're right. This is a phenomenon of discrete time systems. The invertibility of these systems is not guaranteed, except in some interesting cases you can guarantee some invertibility. But what happens is that going back in time in discrete time systems not always gives you a unique solution of the backward process. So it's ill-defined. The inverse of the system, meaning by that the dynamical system will start to trace back your states. Given all the control inputs that you have applied, you will not have in general a unique solution for those states. And this lack of invertibility is sometimes attributed to the fact that the state space is not large enough. And that's why sometimes you need to resort to those assumptions about invertibility. In fact, when you do those assumptions about invertibility, then the problem becomes even closer to the continuous time case, because you are able in those cases to introduce a sensible definitions of Lie brackets and very much parallel the discrete time, the continuous time counterpart. But that requires an invertibility via the control input and the differentiations through the input being able to reproduce the Lie bracket operation. But that's outside the scope of what we were planning to give. So this is the particular case in which you cannot get rid of the U in the zero dynamics, because that requires variables which are not in this state. So the state coordinate transformation that would take you the boost converter to the Isidori canonical form precisely as we defined it is not possible. Because of
okay, I see. But sorry to interrupt. One more question.
Yes, please.
So I want to see if I can write it directly on your whiteboard. So I have a question about the continuous time system and the discrete time system. So if you have continuous time system here, and then you do discretization, you get a discrete times system. And then you calculate, you do some coordinate transform, you obtain its zero dynamics. So this is what you have discussed so far. But I'm curious, what if, so in the continuous time, then we compute the zero dynamics. We got the zero dynamics right here. And then we do the discretization. So we have two different routes, but will we obtain the same result at the end? So in other words, are these two options commute?
Yeah, is this diagram commutative? I'm having a hard time looking at your diagram, but yeah, I think I understand it. Yeah, this is. Let me clarify that this example, I brought it up because it was a physical example. This example does not belong to the class of native control systems, because even though it is switched, it is still a continuous system, physically speaking. So this is a convenient model to do some analysis in discrete time. And given that maybe your computer is capable of introducing piecewise constant control inputs, let's say, and that analysis would still be valid. Yeah, this diagram in general is non-commutative. And
it's non-commutative.
Is non-commutative, yeah.
Okay, okay.
And this issue with the zero dynamics is just one point there in that diagram.
Okay.
To do that exactly as you would do it in continuous time system. Yes.
Okay, okay, I see. All right, thank you.
Okay.
Gracias.
You're welcome. All right, thank you. Okay, so let's design a feedback control for this system. In this case, is very simple. Let's propose this nonlinear feedback control, and incidentally, this has two sources. One is the use of this function in terms of U and eta, sort of gives you a clue to the feedback that you should use, but this is just a coincidence. And so the equilibrium motivates the form of your feedback. That's somehow at the root of what is called extended linearization that was introduced by Champetier many, many years ago in the 1970s and 80s. And so this is a nonlinear feedback. When you use this nonlinear feedback, your output equation is linearized. It's linearized, and you have a stable dynamics. You have this closed loop dynamics when you use this feedback in the linearizable part of the system. So the system is linear, but is forced by this term. So you have your eigenvalue is 1 minus delta over Q, and it's a constant eigenvalue. So if you choose delta over Q between 0 and 2, you will have stability of Z1 towards V. So that satisfies the first objective. Now let's look at what happens to the zero dynamics when you use this control in this equation. When you use that control, what you get is this nonlinear dynamics. And this nonlinear dynamics is very interesting because it has eta 1 dividing here, eta 1 adding here in a linear fashion. And so you can compute the equilibrium point when eta 1 k plus 1 is equal to eta 1k, so that cancels these two terms. And eta 1k is just v squared over q, as we had here. So that conforms to the equilibrium. Now, is it stable? Well, one way to find out if this nonlinear dynamics is stable is to linearize it around the equilibrium point. When you linearize these nonlinear dynamics around the equilibrium point with the help of this incremental variable eta 1 delta of k, you get this linearized dynamics. And this linearized dynamics, no matter what, is unstable because delta is positive, q is positive, is a resistor, is the normalized value of a resistor, which is always positive. Delta is the sampling interval, which is positive, and v squared will never be negative. So the eigenvalue is greater than 1. Therefore, eta 1 delta is always unstable. That means that eta 1 will be growing. If eta 1 is growing, UK is becoming smaller and smaller. And there will be a moment in which eta 1 causes you to saturate to 0. And therefore you're converging to an open loop situation. The zero dynamics does not, affect your control drastically in this case, but it does tend to drive it towards a particular value of the saturation possibilities, which in this case are 0 and 1. Therefore, you know that you have an unstable zero dynamics. The current eta 1 delta will be growing, and you will not notice. You will not notice the growing of eta 1 in the output equation, because the output equation is totally independent of it. In this case, it's linear and is converging asymptotically to the required equilibrium. You will not notice it in the control because the control is just going down within the feasibility region, and that is sort of nice. But the current is growing and starts boiling up and starts cooking the circuit, and you will not be able to see that immediately in the control as an instability of the control, as some growing value for the control, or instability in the output. It's completely hidden, but the current will destroy your circuit sooner or later. So this is one of the issues of the zero dynamics. You have them in all flavors. You have zero dynamics that affect your controller design. You have zero dynamics that is not noticeable in your controller design. You have zero dynamics that you find out too late that it was unstable. So this is a nice physical example. Another possibility for the same circuit is that you have as an output the current. It's not as common, but since everything is measurable in those circuits, X1 is one possible output. So it means you have the zero dynamics will be X2 because X2 has a gradient which is independent of X1, and the linearizable part of the dynamics is here, and the zero dynamics is here and dependent upon the control input. So in this case, there's no transformation to speak about. You just rename your states, and this is the canonical form. This is the linearizable part, and this is the zero dynamics part, and the output is the first coordinate transformation. Nice. Very, very much feasible. Very simple renaming of the states transformation. So if we want to stabilize this to the equilibrium point, which is exactly the same we had before, we can control that now through a nonlinear feedback controller, which is inverting eta 1. And remember, eta 1 is just the output voltage. So the inverse of eta 1 would be a nice feedback controller. And it's again motivated by the equilibrium expression of the control input. The control input is 1 over V. V is related to the voltage eta 1, and therefore this is the feedback law. It's an extended linearization sort of viewpoint, but it's not rigorous, and one should be careful to be motivated by that in general. There are some conditions that were put by Champetier. And so UK has this simple expression. When you substitute that UK in the control expression, you block this term, and therefore C1 is in equilibrium, because the evolution of C1 in closed loop is totally in equilibrium. So if you start with this voltage, you will remain at that voltage. And the zero dynamics is given by this nonlinear function. When you substitute this control input law into the second equation, now you have, in equilibrium of the first one, you will have this expression. There's a nice nonlinear structure, and the stability of this nonlinear structure around the equilibrium point is found very easily, because if you are in equilibrium, these two quantities are the same, they cancel. This should be 0. That means that eta 1 square is just V square, because the Q eliminate, and eta 1 is plus V, because minus V is not physically possible. So eta 1 is plus V. You linearize this system around the equilibrium point for eta 1, and you get this dynamics. This dynamics now is always stable, because this eigenvalue of the linearized dynamics is always smaller than 1. Delta is a small sampling interval, and Q can only get larger, or can be small, doesn't matter, but you know, this is generically speaking for delta and Q positive and smaller than 1, this will be a stable eigenvalue dominating the linearized dynamics around the equilibrium point. So this system is minimum phase. The zero dynamics is asymptotically stable. The previous model, in which we had the output voltage as the output variable, is non-minimum phase. This is minimum phase, and if you guarantee this condition, which is very easy to guarantee, you will have a globally minimum phase system. And this is an interesting thing to know in power converters, because one would tend to use the output only for feedback. Well, it tells you that if you use the output only for feedback, even the most reasonable controller will not be able to get rid of the instability of the current, because that output is non-minimum phase. And on the contrary, if you take the control input, then you will have if you take the inductor current as your output, you will have a minimum phase. Okay, let's give you a small break, and then we'll come back as suggested by Professor Gao. Are you all with me?
Yeah, let me ask, are there any questions from the audience? So Herbert, I have a question here. There's plenty of literature on non-minimum phase system, feedback design method, and so on. According to your presentation, to your material here, if you have an unstable zero, there's always some variables unbeknown to you that goes unstable.
Yeah.
So how does this reconcile with the previous work on controlling non-minimum phase system? Are we saying that doesn't matter how good our method is, there's always something unstable in the system?
Yes, there is always something unstable. The zero dynamics cannot be modified. The nature of the zero dynamics cannot be modified. Of course, in discrete systems, as well as in many continuous time systems, you have local stability, and you can have instability from the outside of some attractive region. And since the nature of the zero dynamics cannot be changed by feedback or any other means, except by changing the output, by considering a different output, then the zero dynamics is something that you have to be very aware of. Because if you can guarantee reasonably initial conditions for that zero dynamics that will eventually converge to a stable equilibrium, that will never bother your controller design. But if this dynamics is out of some attractivity region, as it easily happens in discrete time systems, then something goes unstable, and there's nothing you can do to prevent that, because your control is already busy controlling the system. So indirectly, you cannot do anything with the control to be able to bring that dynamics into due course. And also, sometimes you won't even notice that this thing is going on because you're only accessing inputs and outputs. And from the input-output viewpoint, that dynamics is sort of hidden. But of course, you will suffer the consequences of that instability sooner or later. There are another class of examples in which you live with that instability, and it doesn't mean that things are going necessarily wrong. Let's take a simple physical example. Suppose you have a current, a motor, some kind of motor, DC motor or whatever, and the position of the motor, when you drive your system to a constant angular velocity, the position is growing. The position is growing without any bounds. I mean, the angular position is going very fast at thousands of revolutions per second, going out of bound. But that doesn't bother you. First, because the phenomenon is periodic, and second, because it doesn't have any physical consequences. That's what you wanted, the motor running around and around in a periodic manner for the position, even though the angle is growing without bounds. So this physical fact does not affect you. And in some other examples, and there's an example coming up of a lunar lander, you know that the system is zero dynamics, is unstable, but you make provisions for that so that you...
Excuse me, in your boost converter example, it doesn't matter. If you use the inductor current as a control variable, as a controlled variable, then you're fine. Your zero dynamic is stable. But the the whole point of boost converter is to boost the output voltage. So controlling voltage is the primary problem for boost converter. But according to your analysis, if we do that, the inductor current goes unstable.
Well, that is if you take as the output, the output voltage. That voltage is a non-minimum phase output. And if you manage to control it based only on output feedback, you will be fine in terms of the voltage, but the current will be growing. So, but
wait a minute. That's how boost converter works. You control output voltage.
Yeah,
But
you control the voltage. You're right, but indirectly. You control the voltage through the current, and controlling the voltage through the current makes the whole ball game completely different, because now you have a minimum phase system.
What do you mean by controlling the voltage through the current?
You feedback the current.
Mm.
And you base your strategy on feeding back that output, which is your output, your minimum phase output. So you're doing indirect control. If you control the current towards a corresponding value of equilibrium, correspondence with the voltage, because they are tied, those equilibria are tied, then the equilibrium value for the zero dynamics is stable. If you do it the other way around, the equilibrium value for the voltage is unstable. And so any small perturbation from that particular voltage you manage to control your non-minimum phase output will destroy everything, because the current will start growing very fast.
But for the boost converter, inductor current is an intermediate variable. It's not the goal. It's energy supply to the capacitor, and it charges the capacitor to the voltage you want. So yeah, it's in terms of functionality, it's not critical variable, but in terms of stability, as you portrayed, it is.
It is. And the thing is, people get away with this because they do the following, which is very smart. They put a proportional derivative controller. And what is a proportional derivative controller doing? Is feeding back the output voltage, but it's also feeding back the input. It's also feeding back the inductor current.
Mm.
And because of this, now you have an output that you're feeding back, which is not non-minimum phase, which is minimum phase, because the current is there.
Okay.
This is sort of strange, but
so what are you controlling then? You have one input, which is the PWM to the or not PWM, but which is the input to the boost converter. But then you are looking at two variables you're trying to manage: induction current and the output voltage. How do you manage that?
Well, when you do the proportional derivative feedback, what you do in the derivative term contains the current, even though you maybe not very much aware of that.
So in a way, there's like an inner current loop.
Yeah.
Okay, got it.
That's how it works.
Okay. Thank you. Any other questions? Professor Li Hui is expert in power electronics from Shanghai University of Power. Shanghai Power Engineering or Electric Power. I don't know exactly, but I visited his lab. This is what he does. He does it for a living. So maybe we'll later on get the input from him as to how this would apply to his his problem. And he's maybe you'll have a chance to visit him in Shanghai and develop some more in-depth collaboration. So I don't know if Professor Li Hui is here, but maybe later.
Li Hui? I think he's here.
Professor Zhang is, do you have something to add to it? Professor Zhang Jun.
Yeah, actually, I have a quick question. So here, your control U is actually the duty cycle, right, for PWM?
Yeah, that's on the average, that's what you're doing. But
yeah, but I don't exactly understand how the duty cycle can be. You said you use PD control, right?
Yeah, you do it to generate the duty cycle. You see, the duty cycle now is a continuous variable.
Right.
That evolves between 0 and 1, let's say. It's just the width of the pulse. And it takes continuous values. It's not discontinuous. So what people do is they put a proportional derivative controller to generate the duty cycle. And they give this duty cycle signal to the PWM. And therefore any deviation of the output voltage from the required value or from the equilibrium point will give you a signal that either increases or decreases the duty cycle, and therefore you regulate towards the equilibrium again.
Oh, I see. Okay, all right, thanks.
But you see, the average model, it captures that process. That's why the average model is nice, because it gives you the perfect guide to come up with a controller which is analog in the switch environment. And PWM has also been shown to be totally equivalent to sliding mode control, which is the natural way to control the system. So in an idealization of PWM, when you have infinite sample frequency, the duty ratio becomes the equivalent control. And that's how you get clues on how to feedback controls, especially when you are interested in nonlinear control laws. And you saw here that two nonlinear control laws were very easy to implement on the system because they were coming from the equilibrium conditions. And you just mimicked that equilibrium condition into your active feedback and gives you a nice response. Nice stable response. It linearizes the system. But you do this in the average, and the implementation on the discrete digital part will have no problem.
So Herbert, is this a post-converter problem is a particular example, or is there a general way of dealing with unstable zero dynamics? Obviously here, that has something to do with initial condition. It has something to do with feedback control law, whether or not you should include a particular variable associated with the zero dynamics as part of your feedback. So do you have are you aware of any general treatment of something like this?
Well, one of the ways that we were doing earlier this year to control systems with unstable zero dynamics was to do it indirectly. And one way that is feasible sometimes is the flatness. If the system has a flat output, that's the output to be controlled to get rid of all the instabilities present in the non-minimum phase output. But that conforms to the idea of changing the output. To completely describe a new ball game, changing the output means you don't want to deal with the actual output of the system. You're willing to sacrifice something or invest something in measuring some other variables in order to come up, let's say, with an output that doesn't have any zero dynamics. And that is one way to do it.
So for the literature up to this point, there's really not that much there either. I mean, we talk about the non-minimal phase system, non-minimal phase zero, but we're talking about controlling the state, not the zero dynamic. We're talking about controlling non-zero dynamics, but we leave the zero dynamics alone. I mean, there's I have hardly seen anything devoted to what do you do, how can you avoid it. For example, the flatness approach seems to be the only one up to this point.
Is one of them. There are people who have been producing other possibilities, but in essence, what it amounts to is to change the output. And that completely rewrites the problem. I mean, it's a new problem with an output which is more convenient. Like in this case of the boost converter, the output voltage is not a convenient voltage to design a feedback because it produces instability. So you switch to the inductor current as your output. And it's not as convenient as the output voltage. You don't want to do that. You might do a combination of the two variables, and at the end, that's a new output that has a stable zero dynamics. Yes, you are absolutely right. But people have studied the problem. There are many names that I could mention. John Hauser did some work on non-minimum phase systems along with Professor Sastry on controlling the PV toll, which is a multivariable non-minimum phase system. Controlling the center of gravity leads you to instability. Controlling the center of oscillation gives you a stable design. So changing the output changes the whole picture. And if you have available, that's part of the problem. If you have available a variable which does not have any zero dynamics, then you get rid of all the problem, because that design will be stable. Yes. But you're right. People like Jesse Grisel, along with Maria Domenica Di Benedetto in the 1990s, also wrote a paper about controlling non-minimum phase systems. And the prescription they gave there in that very early paper was change the output. And this was very rigorously done in mathematics. Jesse Grisel is very much a guy that comes from a strong background in mathematics. And many other people, like Michel Flies also was interested in that problem in the 90s. And of course, many names escape my mind, but there are many people that in those days, 80s and 90s, were already working in this problem. And flatness sort of evades the problem.
Right.
Basically the same.
Right. So flatness is the only systematic approach in modifying.
It's one systematic approach. I'm not aware of some of the things that people have been doing, but the essence in which it is based, I don't know, but maybe they play around with the equilibrium of the zero dynamics if they can move it by some other means. But what should come out clearly is by means of feedback, you cannot change the nature of the zero dynamics.
Right. I mean, I'm talking about the fundamental modern control theory. I mean, in robust control, they do mention that what you measure is not necessarily what you control.
Yeah.
So it is well known, but in terms of how do you select the variable to be controlled, there's very little on that. And flatness is one of the only, from what I know, a systematic way of, this is how you select the output to make your life easier. There may be bits and pieces of other people's work, but they do not form a cohesive whole as a systematic approach to select the output. So now we get back to this, the core issue is you can ignore the zero dynamic. We control systems by the relative degree all the time. we never ask ourselves what happened to the zero dynamics. We never, even if they're stable, they still affect the system. Like in your example, they still affect your system in some way. But in your approach, in one example, you said, well, if my initial condition stay within the unit circle, this I'm okay. But if I go outside, then I have trouble. These are the information that can be that should be made aware of by the designer. So we know where are the safe operating region for the control system, even if we have a unstable zero dynamics. So
yeah, in the linear case, you have this wonderful advantage of being able to assess stability by means of a graphical algebraic procedure that finding out the roots of a characteristic polynomial. But in the case of nonlinear discrete time systems, when you have a zero dynamics which is nonlinear, as simple as you know, eta dot is, or I'm sorry, eta k plus 1 is eta k minus eta k squared. You can have a lot of complexity in the autonomous response of that discrete time system. But in some regions, it becomes convergent to the stable equilibrium point. In regions, it just goes wild. In other regions, it starts decreasing very, very slowly. So you have all sort of behaviors. There is a wonderful book by Shlomo Sternberg on discrete time systems, which can be read very pleasantly, almost like a novel at night, because it gives you a tour on the complexity of discrete time dynamic nonlinear systems. Nothing to do with control. It's just mathematics. And
can you on that note, can you give us the reference for that book? And also
yeah, I can even send you the book. I have it digitally. I don't know if it's legal to do that, but I can send you the book.
Yeah, at least I can tell people the name of the book. They can look. If you can find a PDF, other people will be able to, I think.
Yeah,
but
Shlomo
also,
Sternberg, he's a professor in Harvard University.
Yeah, but also you mentioned quite a few papers today.
Yeah, I will post it
about choosing the output. Can you give me a list of those papers?
Yes.
So I will share this with the audience.
Good.
Before next talk, because they want to follow up on your lecture and do more studies. And we understand that it's not convenient for us right now to share your lecture notes because you're still writing the book. But we want to be able to continue to do a deeper study of the interesting, fascinating subject, very fundamental, but very little addressed in the current literature. So we thank you very much for this wonderful lecture today.
Okay, so we should finish it now, yes?
Well, do you have some more to cover? Do you?
Yeah, I have a lot, but you're right. Maybe people in China and somewhere else are tired to continue with the lecture. Let's stop at this point.
Okay, I think that's.
Thank you very much, Professor Gao, and thank you all for attending. If you have any further questions.
Yeah, anyone has any further questions? I think it's a good point to stop because I think this is so fundamental. Everyone should study on it, study, follow up on this important lead before we take it up again next week.
Okay.
Meanwhile, if anyone has questions to ask, please send it to me, or send to Dr. Sira Ramirez directly. That's fine. But especially those experts in power electronics. Professor Li Hui today doesn't have the mic, so sorry he couldn't join us in the conversation. But I very much like to know what the people in power electronics think about this, and if there's something like some insight like this will help them do a better job in designing control laws for power electronics. Any other questions from audience? Okay, so Herbert, let me return the host back to you so you can.
I think I'm pretty much in command now. I think.
Yeah, you
Right.
you are now the host. I still don't know how to make the co-host yet, but
yeah, there used to be an option. I guess when you were setting up your system, they
right.
asked for that option, but it's no longer available after you have set up everything.
Right. So I'll find out.
Okay.
Again, I think.
Thank you very much for attending.
A very nice lecture.
Have a
today.
good time and have a nice weekend.
Thank you.
Take care of yourselves.
Yeah.
Bye-bye.
Bye bye.